66 million years ago, North America was split into two landmasses by the Western Interior Seaway. This was a warmer, ice-free world. High sea levels pushed coastlines deep inland, and with the moon physically closer to Earth, days were 30 minutes shorter. Environmental stress was already present. The planet was in the middle of a long-term cooling trend, and in what is now India, the Deccan traps were erupting, flooding the atmosphere with sulfur and carbon dioxide. Yet dinosaurs remained the dominant biological regime. For 150 million years, they successfully occupied nearly every ecological niche on land, from the tropical lagoons of Europe to the immense coniferous forests of America. This was a globally stable biological hierarchy. While the climate was shifting, these animals were highly adapted to their world, with no biological precedent for a sudden, cosmic intervention. The apex predator of this era was Tyrannosaurus rex. Measuring 40 feet long and weighing 15,000 pounds, it possessed a bite force capable of crushing bone, allowing it to eat hundreds of pounds of food in a single bite. Hard fossil evidence provides a clear window into their biology. We can count growth rings inside their bones to determine their age at death, and the discovery of medullary tissue, a calcium source for eggshells, allows us to identify female specimens during ovulation. Other details remain hypothesized. We debate whether T. rex sported scales, feathers, or a combination of both. Its skin color remains unknown, as does the specific mechanical purpose of its small but muscular forelimbs. While T. rex was a biological masterpiece, biology is irrelevant to the kinetic force of a 6-mile-wide rock. This asteroid was traveling 10 times faster than a bullet, hurtling toward the Yucatan Peninsula completely undetected. Survival would stop being a matter of biological adaptation. In the coming minutes, the only factor that would matter was sheer physical luck. The asteroid struck the shallow waters off the Yucatan Peninsula, gouging a crater over 20 kilometers deep into the Earth's crust almost instantly. The energy released by the impact was roughly 3 × 10⁻³ joules. That is the equivalent of 5 billion Hiroshima-sized atomic bombs detonating at once. The strike triggered magnitude 11 earthquakes and sent tsunamis surging more than 300 kilometers inland, stripping the landscape of vegetation and soil. For every living thing at the impact site, the end was instantaneous. They were vaporized by the heat of the collision before their nervous systems processed the flash. The impact vaporized sulfur-rich bedrock, ejecting millions of tons of debris into the upper atmosphere. As these particles fell back toward Earth, frictional heating turned them into incandescent torches. This created a global heat pulse, raising atmospheric temperatures and igniting widespread forest fires. Animals caught out in the open faced several hours of intense infrared radiation, similar to an oven set to broil. In the Badlands of North Dakota, a site called Tanis preserves the exact moment this catastrophe arrived. A massive surge of water buried the local ecosystem in a thick layer of sediment in a matter of minutes. The mud at Tanis is filled with tektites, microscopic droplets of impact melt glass. These were found lodged in the gills of fish and the bodies of land animals, proving they were alive and breathing when the debris began to rain down from the sky. This record confirms the impact was a global incineration event. The lethality of the strike reached thousands of miles from the Yucatan in less than an hour. Following the heat, the world turned cold. Soot from the fires and vaporized sulfur coagulated in the atmosphere, blocking the sun entirely for several months. This darkness shut down photosynthesis at the base of the food chain. Land plants died off, and the phytoplankton in the oceans collapsed, causing ecosystems to fall apart like a house of cards. The starvation moved upward. With no plants to eat, large herbivores died first, followed soon after by predators like T. rex. The initial blast was only the beginning. The primary driver of the mass extinction was the sudden, total collapse of the global food web. This thin, dark layer of iridium marks the KPG boundary. It is a global geological fingerprint of the asteroid, separating the age of the dinosaurs from everything that followed. The extinction wiped out 75% of all species on Earth. The non-avian dinosaurs, flying pterosaurs, and giant marine reptiles were erased from the fossil record. Large body size and specialized diets became fatal liabilities. Animals that required massive amounts of daily calories could not survive in a world where the primary food sources had vanished. The survivors shared a specific set of traits. They were small, often living in burrows or aquatic environments, and they had generalist diets that allowed them to scavenge on seeds, insects, and carcasses. The event acted as a precise ecological filter, systematically removing the physically dominant while sparing the small, the burrowing, and the adaptable. When the soot clouds finally cleared, the sun returned to an empty world. The giants were gone, leaving a massive ecological vacuum across every continent. The surviving placental mammals began to multiply and evolve rapidly. Without the pressure of dinosaur predation, they grew in size and diversified into the ancestors of the modern animals we recognize today. Ultimately, the asteroid was the ultimate disruptor. By ending the reign of the T-Rex, it cleared the evolutionary path that eventually allowed our own species to emerge.